I gave a version of this presentation a little while back to the Oklahoma Asphalt Pavement Association, and I got up before ready to talk, and the lady from the association says, "Are you going to tell a joke before you get up there?" And I said, "Man, I don't really tell jokes. I'm not that good at it." And I said, "Why do you ask?" And she said, "Well, your predecessor, Dale Rand, came and talked to us once, and he said he'd brought up the fact that Oklahoma had really good aggregates, and we were like all excited. And he said it's part of a program, where we get all of Oklahoma's good aggregates, and they get all of, Texas's good football players, called the Rocks for Jocks program." And I thought, I kind of laughed like he did. I'm like, "Oh, that's pretty funny." He goes, "Don't tell that joke. That's not funny at all." And he said, evidently everybody's still mad about it years later. So I'm like, "Okay, I promise I won't tell that joke." So anyway, I'm going to spend just a few minutes talking about an alternative analysis method and a little bit of stuff that we did looking at some of the cracking tests and trying to kind of get some resolution. We've been doing the overlay tests for quite a while now, and hats off to TTI and all the work that they've done, and Tom and Fuji and that whole group, Labinda. And then here recently, about the last 2.5 years, we kind of handed that off, and we said, let's let a fresh set of eyes look at it. And University of Texas El Paso came in and was going to really look at the overall process. In other words, let's take a look at the test procedure. Let's take a look at the machine. Let's take a look at some alternate methods we could to try to analyze the data. Let's look at maybe some other cracking tests and see where we're at. And so that's kind of what we have been doing, and I kind of wanted to update you on that a little bit. Let's see. So I'll just skip right into it. So we wanted to evaluate the machines, and there was a lot of interest around the country because some other people were really interested in the overlay test, other states, and they said, well, what machine works? And at the time, when we first started, the ShedWorks machine was the obvious machine because that was the only one. And so, but after a while, others got involved. ShedWorks stopped making it. They sold out to Troxler, so Troxler was making a machine. There's Cox & Sons makes a machine, and it's kind of I guess a venture between Cooper and Cox. I don't know who owns who, but I keep hearing both companies' names, but they make a really nice machine. And then ICP Global made us we have an AMPT device, and they have a fixture that will run it like you see one you see there in the vertical position. So there was these 4 machines, and we wanted to go through and spend and do a lot of work to analyze what was going on with the machines. We also wanted to look at some other cracking tests, like the semicircular bending beam test. That was being done in Louisiana and Illinois, a couple versions of that. There was also the DCT test, which is a disc-shaped tension test, and that was done out of Illinois as well. And then, of course, there's the 4-point bending beam test, and that was being used by quite a few people. Didn't appeal to us because it takes so long to run it, and we still had a lot of variability in that test. So I think one of the things that we struggle with, well, let's just say this, when you look at the overlay test, we really like the fact that you could differentiate mixes with this test. I mean, that was proven out in the very beginning of the work that TTI had done, but we were still struggling with the variability, and we kind of wanted to take a closer look at that and say, what's going on with the variability? Is there anything we can do? And we'd done a bunch of research to look at this, but I think the idea was, let's either, make a decision about the overlay and move forward, or let's look at another test and see how we progress from there. So we tried to go into it with an open mind. But this is the issue that you run into. Let's say we got 5 samples, and we've ran these 5 samples, same exact mix, and we run them on the overlay, and you end up with, all these different number of cycles. And the issue is, well, do you average them? Which one's right? Does it lean, and all of a sudden you can go through all this analysis to try to figure out what's going on. But if you look at the way this propagates, or the crack comes down here, they're all kind of the same, right? But so why are we getting these different numbers here? And so this is where we wanted to really take a closer look at that. So we wanted to look at the precision of the load cell. maybe some integrity issues with the load frame. Maybe there was something going on with the load frame, especially with stiff mixes. We also wanted to look at the analysis procedure, this 93% reduction in failure criteria. That was something that we thought maybe we could look at a different way to analyze, and we ended up doing that. And then also kind of re-look at the specimen preparation again. So we wanted to look at all those things. And this is one of the things that if they first started doing, said, let's look at not only what's going on with the specimen, but let's look at, maybe it'll tell us something about the way that the specimens are reacting when they're being loaded. And so what happens is when you, they mounted this LVDT on top here to measure what was going on top of the specimen. And so really the takeaway here is as the material goes from soft to hard, all of a sudden the top of that specimen goes from tension into compression. So in other words, I'm pulling this specimen apart with the machine, but the top of it's going into compression, which to me is like didn't make sense, but that was kind of what was going on with the specimen. So we felt like there might be some issues not only with how this was bonded to the plate, but also maybe there was something going on with the load frame. And we found some of those issues too, where we were getting some compliance in the machine. The mixes were so stiff, and you know what our mixes were looking like, especially the ones that were going 1 or 2, 5 cycles. They're very stiff, and all of a sudden they're bending this frame. They're so stiff when you start to try to pull them apart. So that was some of the issues that we were seeing. Keep thinking that button doesn't work. Oh, I got it here though. All right. I just keep catching myself trying to point anyway. There was also some improved gluing method. We wanted to look at a stronger glue. That was one of the ideas that UTEP had come up with, because we just wanted to make sure that there wasn't any slippage or breakage or cracking in the glue itself, that there was a strong bond between the plate and the specimen, so that we kind of took all that out of the equation. And we found out that the 4,000-pound glue really did work better, and that's kind of our thought. But and of course, you know, we did also go back from a 10-pound weight to a 5-pound weight. And the reason that we did that was when we talked to the glue manufacturer, they said, well, you need a thicker membrane of the glue. We think you're squishing too much glue out when you put the 10-pound weight on. And I thought, well, that's just a glue manufacturer wanting to sell glue, right? They just want to sell you more glue. But once we went through the process, you know what? It's right. There needed to be a solid film between there to make sure that you had good bond between the specimen and that plate. And also the thing is too that and this was kind of a simple thing. We started doing some analysis and realized just by cleaning the excess glue off the edges, that made a difference. In other words, this one you see here where it's cleaned up, and this, see, I did it again. If you see this one, this is what usually happens is when this glue came out to the side here, we were starting to see stress concentrations out here on the side. I didn't think it made any difference, but you start to analyze that data and you realize it did. It started to make a little difference. So, you know, the guys at UTEP were going, oh, that's easy. You just take your finger and clean it off. And so anyway, simple things, but it makes a difference in how, you know, the data is analyzed and how much variability it has. So some of these simple things, but I think all those things we did leading up to this part really were just seeing minimal improvements in the variability. I think what really was kind of key is this looking at a different way to analyze and characterize the performance of the mix. So the new methodology that we came up with here and that UTEP kind of came up with was really going back to the first, I guess, some of the first work that was done on the overlay test of TTI, and was basically looking at the separation of the crack initiation, which the start of the crack, and the crack propagation, which is the growth of the crack. Those are two different phenomena that was going on, and really to analyze the data, we needed to separate those. So if you look at crack initiation, this is how this is the hysteresis loop here of the first cycle. And so in other words, you're looking at really fracture energy. If you go back to fracture mechanics, you're looking at the fracture energy. And this is really critical fracture energy here because you're doing it at the peak load here. So you're taking this area here, and that's really saying this is the point at which the specimen starts to crack, okay? And so there's a way to go through there, and you analyze that, and you get this data. And by the way, I didn't mention this, but we're not running the test any differently. We're just analyzing the data differently. So everything, all the rest of the parameters, the way we run the overlay test is the same. Makes it nice because you can go back and look at old data and just reanalyze it with the new method. So anyway, so you've got the crack initiation part, and that's how that first crack starts in the specimen. And then crack propagation, or how the crack grows, and we're calling this the crack progression rate. But I think one of the things that we did was we instead of looking at the load at each cycle as it reduced, we were looking at a reduction between two consecutive loads. And so when it got below a certain threshold, that's when the test shut off. So anyway, it's what we do is it fit really nice with a power curve equation, and we put that through the data, and this is really the number we're looking at is that exponent here, that B, and that really gives us this crack progression rate. So what does that mean? You know, we took this fracture energy and the crack progression rate, and we plotted together to kind of give us a visualization of the overall performance of the asphalt mix. And for the fracture energy axis, we were seeing values above 1 were considered better, meaning that they had more resistance to the initiation of the crack than with mixes with lower fracture energy. And then for the retardation rate, or the progression rate now that we're calling it, we had kind of 3 zones identified. So if it was less than 0.5, that rate, then we were saying that was a good crack attenuator. If it was between 0.5 and 1, then that was average crack attenuator. And if it was above 1, then we were saying that's poor. So what does that look like? You look here on this, and really you're saying, okay, this direction here is more flexibility for how the crack grows. This here is basically kind of like a toughness. How tough how much energy does it take to start that crack? And so when you have these two here, you kind of go through and say, this is the zones that we kind of classified out as more crack resistant, less, and then this is the poor mixes over here that don't do so well. So what does that mean? You know, I think that's the next question. Is like, okay, now we can kind of define that out. And the next step we wanted to say was, okay, what does it look like from a coefficient of variation when we do the analysis? And does it still differentiate between good and bad mixes? And so when we did the new analysis method, we were seeing our coefficient of variation below 20%, which we were very happy with. A lot of them now are even lower than that with the improved gluing method. But how does it, I guess back to the question, how does it relate to what we currently do? And this is not an exact science, but roughly we're saying that we first came up with this 0.5 is about 300 cycles. That was kind of our criteria at first, and that was based off that early work that TTI did. But when you put this out, you can see where some of these number of cycles to failure come. So, and you're probably saying, well, shoot, 1,000 is as high as we go. Well, 1,000 is where we cut the machine off. I mean, there's a lot of the mixes that are out there that will go a lot farther than 1,000 cycles. So this kind of runs the gamut, but you can kind of see where that plays out. And so that number of cycles roughly relates to that progression rate. So what about the fracture energy? And we thought, well, it doesn't really relate to that. It didn't relate well to that peak load. It was something else going on with that was defining that. And what we found out that let me go back. It really tied closer to IDT, a little bit outside of our spec limit, the 85 to 200, but roughly 1 is about 75 on PSI on the IDT, and 3 was about 200 on the IDT. So it kind of relates to that number you get off the IDT when you run it. just to give you an idea of how these parameters work. So, so we took all of our mixes that we currently had, and we these are all averages of different mixes that we run. And I know you can't, I'll point out a couple of these, but if you notice, most of these are in this good zone. And these are all of our specialty mixes. These are the TOMs, these are the SMAs. You know, these are a low, and some of the dense graded and super paves here, and then you have a couple of these outliers. Now, we're not saying all those mixes are bad. We're not saying that because these are averages. There were some that were definitely way in that we thought were good. The idea here is now that we kind of have an idea of what this looks like, we can say, okay, how do I get this mix, which is a type C mix, over to this area? Or how do I get this mix, which is a type B mix, and move it up into this? You know, kind of be able to work with the materials that you have. How do I make them more crack resistant? What do I need to do to move them into the different areas to be able to? And so we kind of maybe thinking about tying these things, number one, tying these areas to the type of roadway that you want to put it on, right? You don't necessarily, if you're going to do an FM road, if you're low traffic or whatever, you don't have a lot of truck traffic, you can use some of these areas over here. But if you need something that's higher traffic, that's going to have more demand on it, a lot more trucks, you're going to want some of these mixes over here. So I think we're still kind of working on that, and that's kind of the idea of how we move forward. The other idea is, you know, we kind of like the idea, and I talk about this. I've called somebody out, like say, for instance, Brett. Let's say that you're going to you run marathons? Let's say you're going to, yeah, all the time, okay. Well, let's say you don't. Let's say you don't run marathons, but you're going to train to run marathons, right? And so what you would want to do is to go to the doctor and get a checkup to say, where am I at? And he's going to tell you, don't go out and run a marathon, but start slow or whatever, or here's what you can do. You want to kind of get a checkup. And I think there's a way we can take this information, take the Hamburg information that we get, take some other, you know, common tests and say, let's do a checkup on a mix and see what it does, see what we can do, where it is now, how we could improve it. So I think there's a lot of opportunity there. So that's just some of the ideas that we've been thinking about. But in summary, I think we've looked at this. We prefer the overlay test over some of the other cracking tests that we saw. Some of these other tests are good. We like this new analysis method. It's really given us a better coefficient of variation. All these materials that we've looked at have been 20% or less. The nice thing is you don't have to run the test differently, so all the old data is still good. We've gone back and looked at a bunch of that data to see how it pans out, so we'll have a bunch more data to kind of put onto this. And the overlay test is a cyclic test, which means you're going to be able to take those coefficients and plug them into, you know, a pavement design cracking model, which is very important as we move to like TexME and some of the issues associated with it. You want to have that. You need a cyclic test to be able to do that. And so moving forward, right now we're doing some shadow specking. We're running the new analysis along with the old analysis, collecting that data just to kind of see where we're at. We're going to go ahead and update the test procedure as far as the gluing part of that, kind of get that finalized so everybody can start doing that. And then there'll be some training that goes out. I think a couple people have already been interested, districts that want to get an overlay test. So we kind of have to get everybody kind of trained and make sure that everybody's on the same page as we move forward. So that's kind of really where we're at. We're kind of excited about it, and I think it's a step in the right direction. So I like this new analysis method. I think the hard part's going to be how do we sell that, you know, if that's the right word. How does that make sense to everybody? And when they say, well, you got a 0.5 and a 2, you know. So anyway, that's going to be a little work that we're going to have to do, and we'll get together with TTI and some of the other guys and kind of brainstorm that out. How does that work, and how does that fit into a specification? So with that, that's all I have. If anybody has any questions. Yes, sir, Magdi. Yes. Say, I'm not following you. So I know what you said, but,
Using the average use percentile.
okay, instead of the average use percentile, okay. Yeah, we can definitely look at that. Any other questions?
Hey, Robert,
Yes,
I just kind of encourage you on that training business.
yes, sir.
I really think that's one of the areas to be wacky because it's not a simple test. You know, with all the steps you have to go through. That's what we found. You can get one guy trained.
Mm-hmm.
When you're training technicians, stuff needs to move at a good pace. So I just didn't know if something like Texaco would get involved. Because, you know, we train people how to base tests. Would Texaco be interested in that's hard.
So the question was, Tom brought up the question about training and how that's important, and was wondering if, what the options are, if Texapa would be interested in it. I totally agree. I think they probably would. And the other part of it we would like to do, I think we'd like to kind of copy the program that we have for the Hamburg, where we have an approved list. In other words, you have to go through and do proficiencies every year, and you have to make sure that you've got qualified technicians that know how to do it. So I agree that that's vitally important as we start to get more machines out into the market. Yes, sir. The question was, have we looked at, am I correct? I think I heard you right. How we looked at the different machines and how they compared. I'll say this and to be nice. So the ShedWorks has been fine. That's been a great machine. The problem is that sometimes we were having some issues getting support because they sold out to Troxler. Troxler has had some struggling they've had some issues getting the machine up to where they want it. The AMPT, the work that UTEP did, they went back and they're on their third generation fixture because we were seeing some bending moments in that fixture, and I think the guys that have that AMPT, as we do, noticed that as well. So there are still some issues that we're trying to work out. I'll tell you, the machine that's really been solid and they've worked with us is the Cox & Sons machine. It's a beast. I mean, it's a really good, strong machine. It took a little while to get that machine up where we wanted it, but they've done pretty much everything that we've asked them to do as far as making adjustments and making changes to the software as well as the hardware. But the load frame, there's no compliance in that one at all. So where we were seeing some of that in that early AMPT fixture. Did that answer your question?